Good morning, everybody. If you haven't got your exams back yet, we may have time after class for you to grab them from me, or you can come see me at office hours or make an appointment, that kind of thing. The grades you'll probably see are question by question on the short answer. I'm going to try to figure out how to let you know which multiple choice questions you got wrong, because you are going to have an opportunity to get some of those points back. And I'm like, so I want you to click in. This is a really important part of your reflective problem solving process in this class. Is I want you thinking about, when I went into the test, how did I think I was going to do, and then what does my grade show, or how did I feel after the test? So make sure to click in which one of these you performed much better than you thought you were going to, you performed as well, or you performed worse than you thought you were going to. Please click in your response. Okay. So what I want to talk about for the first 5-ish minutes of class is how to make this align better. The mean score on the test was 71, median 71.88. That means that there is a relative distribution. There was actually, like I mentioned in the announcement, kind of two populations that I saw. Those who did relatively well, and relatively well in general chemistry is anything above 75. Typically, it's kind of like a rough line. That's like you're either coming in with strong skills or you're figuring out how to work within the skills. If you're lower than that, I want you thinking about, what do I need to do in order to get a higher showing than that? So let's go through a couple of different things first. And by the way, I like to show the distribution. So the scores range all the way from 40 up to 100. There was kind of two groups. Like I said, this group here and then this group here. And I want us all thinking about how we know what we know, and then how that relates to how we take tests and how we prepare for tests. So let's start out with this question. Go ahead and talk to your neighbor about these two questions. How do you know when you know something? And how do you know when you don't know something? All right, can I get some volunteers? How do you know when you know something? How know when you know something? English, not know when I know something. Jason?
I believe you know something if you can actually teach it to somebody else.
Fantastic. What are some other examples of when you know that you know something? Great.
Like regardless of how the question is made, you understand the concept, so you can manipulate the words in your head.
Great. So you can either manipulate the problem to come up with other versions of the problem yourself, or if you see multiple versions of the same problem, you know they're related and you can answer any version of them. Fantastic. Eric?
As you read through the problem, you're already forming the idea of how to solve it in your head.
Great. So as you're going through it, you have some ideas of how to answer that question even before you get to the end and see the whole thing. Christina?
Like, when I get bored doing something, so I've done it so many times that I'm confident in it, so not really bored.
Okay, so yes, sometimes when you've done enough repetition that you get bored of it, then you know how to do something because you see it and you're like, oh, I got this. But careful, because the equation sometimes people use is if I spend enough time on it, it knows I know it. It means I know it. Is that true? Spending time studying does not equal performance. And so especially on exam 1 in general chemistry, I get a lot of students that have come up to me in the past and have said, look, I spent 40 hours studying for this test, I got a bad grade, something's wrong with the test. And my response is usually to ask about how they studied, what they did. And did they identify what it is they know? Did they identify what it is they don't know? And where do they spend their time? So on these two, once you identify what it is you know and what you don't know, which one are you going to spend time on? The stuff you don't know. It sounds really obvious when we say it, but a lot of people will reread all of their notes. They'll go back and read all the chapters, and that's how you can spend 40 hours and not become stronger at problem solving in the way that you need to for a particular assessment. What are some other ways to figure out if you don't have someone else to teach? How do you figure out if you know something? What do you do on a regular basis? When you're studying for this, how do you know I got this, I can move on?
I sometimes write my own questions, and if I know how to write a question and then answer it, I usually have a good idea on the concept.
Great. Writing your own questions. Fantastic. What else? What are some of the more normal things that we do?
Practice questions on L.
Great. So there's a whole set of practice problems. And not only practice, but probably the homeworks as well. You can go back and you can practice the homeworks. You can practice all the questions from the chapters that haven't been assigned as well. Do you know if you know something by just thinking about it? Sometimes.
Philosophically, yes.
But a lot of times if you don't crystallize it, you can be like, I got that. Especially if you look at old work that you've done. You just look through the class worksheets that we hand out, and you look through how you solved the problem, you'd be like, yeah, I got that. But unless you take yourself and put yourself in a situation where you're doing a new problem that's the same type or a different variant of that question, you're not going to know whether you actually know something or not. How does that then relate to how your teacher knows when you know something? Okay, an assessment, like a test, is one of the big ones, right? And so I wish I could sit down with everyone individually and talk through these concepts. But unfortunately, in the American college society, we don't have that student-to-teacher ratio. If you guys were graduate students in my lab and I had 2 people, I would know very well what your capabilities were just by talking to you individually. But that's not going to happen in this class. So the only thing I can do is try to help you get there as much as I can before the assessment that I give that's uniform across everyone, and the test is usually that. Sometimes there's projects. A lot of times I can talk to students in office hours or after class or hear their questions, and I can know that they have a pretty good grasp of things. And so if that doesn't translate to the assessment, to the test, if that distribution I showed you at first had no one that got above a 70%, then that would mean that there's a huge breakdown on my part of the assessment. Because there's a distribution of students across the board, that means that there's, maybe I could be more clear, yes, because some of the students didn't do great, but there's also some consistency between my assessment and how students are performing. So all of this kind of comes to thinking about how we study, where we put our time. And I really want to make sure to emphasize that as you're studying for a test, last week I expected to have a lot of students in office hours. If there were parts of the classwork you didn't understand, I think I had 3 students last week that came to office hours. And that's one of many resources, right? I'm not saying that's the only resource that you have. So in order to help us reflect on how we know what we know, and how to prepare more than the week before the exam, I want to encourage you sooner rather than later to spend time with the exam and look at what did I get wrong, why did I get that wrong, what's the right answer, and why is that the right answer, and then reflecting on all the resources we have in class and which ones you utilized. So there's, originally in my syllabus, I said that by the end of the semester, if you show me you know the material, then you can earn some of the credit back for that. I worry that that means that if students didn't have the score they wanted now, that they would be discouraged and they would put it off until later. Chemistry is a class of cumulativeness. Everything builds on previous material in Gen Chem. And so if you put this off until later, it means you're going to be underwater and you're going to stay underwater until some point in the future, at which now you have multiple tests worth of material that you're not comfortable with, you've lost your confidence a lot more. So I was trying to figure out yesterday what's the most effective way to motivate people in this class to go and look at that exam as an example of knowing what you know, knowing what you don't know, focusing on the things you don't know and relearning some of those. And the best way I could think of was to give you 2 options. I can't do both. I can't say on the final exam I'll give you credit back on the stuff you didn't know now and let you get it back now. So you're going to have to choose which one you want. So the way that I'm doing this is if you did well enough, and I'm not saying the people that decide not to do this can't still get some of the credit back. This option still applies. This is the final exam. If you show me you know it on the final exam, you'll be able to get half the credit back. And that's what I had envisioned doing normally with what's written in the syllabus. But this is the new option that I'm giving you. And the new option is, and Sam, maybe if you can set 2 stacks on the back table so that when you walk out, you'll grab this. I don't want you focusing on the details of it right now. You can ask questions later, but there's a descriptive assignment, if you will, that has you go back, look at exam 1, identify why your answer was wrong, what the right answer is, and how you would answer that. And then a couple questions about how you studied, what you would do differently looking at your assessment now, so going back to that first question, how do you align what you think you're going to be able to do with what you are able to do? And I hope as you go forward through the semester, those become closer and closer together. So this one, if you decide to do this, exam wrapper is what I'm calling this assignment, then any question that you got wrong is game for you getting half the credit back. That means if you got a 20%, you could get 40% of the points back. It's not a gimme if you write it down, you're going to get the points back, right? You have to show me that you actually went and learned it, and then you're doing that now. So I want to see students in office hours. I'm going to have extra office hours, probably extra office hours on Monday and Tuesday because this is due Wednesday. I'm going to try to do some probably as well on extra on Thursday because I have some at 2. So I'm going to give you guys a lot of opportunities. Come talk with me. We can talk through the problems. You'll see the layout of exactly how that goes. And the question that Joey probably has is, well, what about the multiple choice? How do we know what questions we got wrong? Is that right? So I'm still trying to figure out how to parse out the multiple choice data, but hopefully before early afternoon today, I'll figure out how to send you basically a string of your answers and highlighted red which ones you got wrong. So I'm not going to tell you the right answer. You're welcome to talk to your friends in this class, your colleagues in this class, and see what they did and how they did it. But a big part of the way you're getting credit back is by showing that you understand why your answer was not right, and then why the correct answer is right. So even if you know the right answer, it needs to be more than that, and there's 2 questions written out on that form. You have to answer for every question you're trying to get half the credit back for. Another question?
Why can't we just get our scans on back and turn it in?
Because it's not about just re-answering the question. And so, well, one,
But it'll tell us what we got wrong. So
does it actually scratch it off?
it'll mark it.
Okay. Yeah, that would probably be an easier way than what I was doing. What I was doing is I was doing Excel formulas to match and code red and all this. It was a pain.
Any other Scantrons that I've ever taken, they mark them.
So I'll check it out. I'll go right after this and I'll go collect the Scantron, see if that's an option, and then you can collect those for me. Does that sound good? Good suggestion. Thank you. All right. Any logistical questions on this? I'm going to ask that you guys do outside of class just because we've already spent 15 minutes on this, and I need to make sure you're prepared for your building on your Lewis structure lab that you're doing this week. So in this first part of class, I want students to be able to, by the end of this, let's see if I have a headphone jack, to be able to contrast the energetic consequences of breaking and forming chemical bonds, and to explain the energetic consequences of, or the energetics of common biochemical reactions like ATP hydrolysis. So far we've talked about individual atoms, and we've talked about how atoms have different numbers of electrons based on their charge. If we're talking about 2 neutral atoms coming together, you've probably seen this in some capacity before, but I want to specify the way in which atoms end up interacting with each other is they can either transfer an electron from one to the other, so we end up with a positive charge on the left here where we transfer an electron from it, and a negative where it transferred to it. Why would the sodium give up 1 electron? Can I have a volunteer? Kiana? Because it's in group 1 and... Who was saying that? Is that Joey?
It gets closer to the noble gas.
Great. It ends up with a noble gas configuration. And why does chlorine accept 1 electron? Say that again?
It needs 1 more to fill the channel.
In order to be isoelectronic to the noble gas, it can accept 1 electron. Okay, so that's one way in which we can increase stability of atoms, is losing or gaining electrons. But that doesn't always happen. A lot of times, atoms can be more stable just by sharing electrons, and it ends up counting similarly towards a full octet or duet. And so here we have chlorine and bromine. If each one of these shares 1 electron with each other, then it is a similar stability increase, and it can be somewhat like it's gaining the electron itself. And so we're calling these ionic bonds, we're calling these covalent bonds, and then we're not really going to be talking about how metals bond because they have a whole different way that all the electrons are shared, kind of in a C formation instead.
Does it always matter with metal, non-metal?
Yeah, so there's a big trend that if you have metals and nonmetals, you'll typically see this kind of bonding.
Ionic.
And so that relates, yeah, exactly, ionic bonding. And that relates to electronegativity. And so the electronegativity is one of the trends we didn't really spend any time on. But the basic idea is that the top right corner, fluorine, is the most electronegative atom. That's when they're bonding, when they're sharing electrons, it's how strongly each atom pulls electrons towards itself. Metals are some of the weakest at pulling electrons towards themselves. And so if we have two that are relatively close together on the periodic table, it means that they're going to be pulling, both of them have a pretty strong desire to pull the electrons, so they're going to end up being shared. Versus when they're on opposite ends in the periodic table, one is going to rip the electron from the other, and that's going to be a very unequal sharing. So with that in mind, we can think about when we have covalent molecules, that those molecules are kind of, you'll be playing with them in the lab this week, but you'll see that there's connections between them. Those connections exist because they end up increasing stability. We'll spend some more time with that. And what we're talking about today is specifically if we have a molecule where those atoms are bonded together to increase their stability, we're not talking about how one atom interacts with another atom. Right? So it's how the atoms in this molecule are interacting with each other, as opposed to this molecule interacting with this molecule. And so this attraction between two different atoms really exists for two different reasons. The electrons from one are attracted to the nucleus of the other. We have two hydrogen atoms, for instance. Those hydrogen atoms are pulling the other electron from the other atom towards itself. Why are those atoms not coming all the way together then? Think about it for a sec. Actually, talk to your neighbor. Why do those two atoms not come all the way together if electrons and protons from opposite atoms are attracted to each other? Can I get a volunteer? Why do those atoms not come all the way together? Aaron? What's repelling each other? Okay, so the electrons, if we think about quantum, are actually spread out over a very large space. So the repulsion between those, until we get into some bonds, which we'll talk about in a little bit, are not actually the main driving force for keeping atoms from colliding. What is? Love?
The positive nucleus.
So the nucleus is a point source of positive charge. And so whether it's one proton or lots of protons, those can only get so close together before they start repelling each other and they start pushing each other away. So the electrons, protons interact and pull each other closer. Protons will repel each other. And so there's a couple different ways you can look at this. You can look at the main electron density. So where do these electrons end up? They end up kind of close to the nucleuses that they're together in that bond because they're attracted to both of the nuclei. And you can kind of look at it as a density of where the electrons are with the two nucleus. Just a different way of looking at where the electrons end up staying. So let's watch a quick YouTube video. Why is this not?
With molten potassium chloride.
So let me go back to the very beginning so you hear the audio.
If we combine one gummy bear, which is composed mostly of sucrose, with molten potassium chlorate, a violent reaction occurs. A surprising amount of energy is released by the reactant, and in the process, their atoms and molecules rapidly rearrange to form the products carbon
It actually
dioxide,
sounds like that.
water, and potassium chloride. The reaction is said to be product favored.
Right.
It's kind of an understatement, right?
Yeah.
So, just to clarify, molten potassium chlorate is basically just a source of oxygen. And there was some energy there as well.
It is a large source of oxygen.
So, if we have this reaction, we have a sugar combining with oxygen. Do you guys remember what products are? Said them right?
Carbon dioxide and water.
Carbon dioxide and water. And we're not worried too much about balancing those yet. We'll be spending some time next week on that. So, if you were to describe this reaction, is the gummy bear releasing energy or absorbing energy? I have a little picture of the gummy bear in case you don't remember what it looks like. All right. So let's see what everyone decided to say. Why do we think that the gummy bear is releasing energy in this process? I hear some new voices across the class. Go with your gut. Savannah? Okay, so we're not getting to that level yet. So just from the video, what cues do we have that this reaction, the gummy bear, is releasing energy? John?
Heat is being produced.
Okay, we assume there's a lot of heat being produced. There wasn't there to start with, but yes, there's also heat being released. New voices, new voices, new voices. Taylor?
It's producing CO2.
Okay, so it's producing product, but we don't necessarily know that that's releasing or absorbing energy. Matthew?
It's making a lot of noise.
Making a lot of noise. Great. And?
A lot of light.
Great. So light is being released. And we talked before about if it's absorbing light, that means it's absorbing energy. It's releasing light, it means it's releasing energy. All right? So I agree with you guys. So where else are gummy bears burned? In their stomachs. Great. And what do we call that process? Let's be more specific. What do we call the process of burning gummy bears in order to gain energy? So it turns out the chemical formula, the overall chemical formula, if we simplify it, is the same exact thing as combustion. So combustion and metabolism are basically the same process. And so how does our body harness energy? Because we don't have a belly full of fire, right? And we don't just have a little like steam engine going.
It's a catalytic process. It has to be.
So if I get a hand raise, how does our body harness that energy that comes from burning the glucose? Josh?
Well, there's two different forms, but there's the acid in our stomach will cause a chain reaction to break apart a lot of some food sources, but once it reaches our large intestine, we have a lot of bacteria. And
The question is, where does our body harness it? Like, how does our body harness it and store it?
glucose in the blood.
So that's what it is, but it has to go through a breakdown process, and then at some point our body stores energy. So how does our body store that energy? Amber? Okay, so fat's one of the ways, but there's an intermediary. Eric?
Adenosine triphosphate.
ATP. All right. How do you think chemists like this diagram of ATP?
Love it. It's easy to see.
Kind of like Pac-Man, right? So chemists like to show it like this. So we have an adenosine, we have 3 phosphates connected, and this is a place in which we store energy in the body. I think if you've had a biology class, you've probably spent a little bit of time talking about this and metabolism and how they relate to each other. If you haven't, hopefully you've heard of ATP. And if you Google ATP, this is one of the first images that you get. This bolt of lightning and then this big poof. And so without saying anything aloud, I want you answering this question. We're going to spend some time exploring this. we're not going to talk to our neighbors about the answer to this question yet. A couple more. Closing out. Submit, submit. Good? All right. So here's where the majority of the answers lie. That we have this flash of lightning, there's this release of energy. Okay? So in order to explore that system, I want us thinking about the simple system we talked about just a few minutes ago, talking about two hydrogen atoms. We have two hydrogen atoms. And by the way, in the lab this week, you'll get to play with multiple kinds of model kits. This is one of them. And so there are magnets that kind of mimic how atom attraction happens. And so we're going to talk about if we have a hydrogen molecule versus two hydrogen atoms. If we start with two hydrogen atoms separate from each other and leave them somewhere in space, the question is, we're going to use a simulation to show how this actually happens. So the simulation, just to orient you, there's two atoms right here. One of them has a pin in them and is not going to move, this left one. The one on the right is free to move. We're holding it still, and at some point we're going to release that pin, or release the one on the right, and the question is, what's going to happen to it? Up top, there's also a diagram. I should move this so you can see it. All right, so this diagram is related to the atoms below. We have one of the atoms on the right is that blue dot that's on the line. So I want you to think about, let's do think, pair, share. That means think on your own for 20 seconds, then talk to the person next to you, and then I'll ask for some share outs. What's going to happen when we release the atom on the right? So think about it on your own first, then you're going to talk to the neighbor, and then I'm going to ask for volunteers. So you can put your hands down because if it's about this, I'm not going to hear from individuals yet.
I'm just trying to figure out what
You want to clarify? These are going to be two hydrogen atoms.
Okay.
Okay, so go ahead, if you thought about it, talk to your neighbor. Go ahead and answer the first question. When we release those two atoms, they're going to go further apart, come closer together. All right. It's a little bit different coloration because they changed the simulation, so I took that screenshot. But here's our two atoms. Here's the one that we're going to release. Okay, so I'm going to have a hand raised for someone to volunteer what happened, and then a second person to say why that happened. So, what did we observe? What happened? Kevin?
They got closer together.
What got closer together?
The hydrogen atoms.
Great. The two atoms got closer together. Did they smash into each other?
Yeah. Yeah, they look like they're still smashing right now.
Okay, so they didn't actually. How do we know they didn't? What about this tells us, Trippy?
There's some distance, like the distance still has one.
So if it went to 0, they would have smashed into each other. It didn't. Why did the two atoms not smash into each other?
The charge is right.
What part of the charge?
The protons.
The protons in each of the nuclei repel each other, so there's only so close we can get. Okay, so this is going back to what we just talked about. Okay, the second reason is why. Why did they come closer together? Gail?
Alright, because they only have one valence electron, so they want to complete their octave.
Okay, so in this case it's a duet, but same idea, right? And so there's an underlying term that I really want to use to highlight what Gale said. So Gale said that they each have one valence electron. If they had two, or looked like they had two, they'd be much more stable in their configuration. Stability is the word I want to use. Okay? So those two hydrogen atoms are less stable apart than they are together. And so when they come together, they increase their stability. Is there anything graphically we can see that also helps us predict that? Did anyone notice that? Hello? So the potential energy was up here. It ended up decreasing. All right, so let's keep that in mind. Let's go back to PowerPoint. So then let's close out this question, reopen the next question. So then let's think about the energetics of that. When those two hydrogen atoms did come closer together, are they releasing or absorbing energy? So think about it for a second. You're welcome to talk to your neighbor about this one, and then click in your answer. A couple more clicks. All right, closing out. Well, before we close out, I do want to see the results. 50-50. Are the hydrogen atoms releasing or absorbing energy? Who wants to defend their answer? Let's hear from someone who hasn't talked much yet today. Logan.
So, when they get closer together, I would say that they're releasing energy because, like, they're constantly moving, so, like, you can't move without energy.
Okay, so one argument could be that as they are in space, they're always kind of moving around. And then they move closer together. So then, I'm not sure whether that supports or refutes your argument. Let's add Trey's voice.
Just from, like, typical engineering stuff, when potential energy goes down, kinetic energy goes up. So that's a release of energy.
Great. So one of the ways that we can answer this is that we saw that the potential energy of the atoms decreased. Where does that energy go? We have to have conservation of energy, we have to have conservation of mass. So those two atoms were apart, they had potential energy, that potential energy is now less, so they release energy. Is there another way we can think about this? Angel?
Just thinking about the electromagnetic spectrum and how when they go down a level, they're releasing energy, and when they're going up, they're absorbing energy, and so would it give off light?
So it doesn't necessarily give off light when we form a new bond. It can release energy in multiple forms, and light can be one of those, and so we saw the glucose reaction does release light when we do some bond formation. The other thing I want you to think about is this model kit does a really nice job of when we take these two atoms. Can you guys hear the click? So the click kind of signifies that energy that forced them together. So they're more stable together, they're in a more stable configuration afterwards, and that they actually release kinetic energy. You can hear the click occurring when they come together. The other easier way to think about it is they're more stable together, right? If they weren't, then they wouldn't be sticking together to each other. So increased stability means that they went through a process to get to the most stable point. You can think about like a ball rolling downhill. The ball is more stable at the bottom of a hill than the top. So when it gets to the bottom, it releases energy along the way. Questions on that? So when those two hydrogen atoms came together, they increased their stability by partially filling their duets. They had an attraction between electrons and protons, so they ended up being more stable and releasing energy in the process. What does that mean about when we pull them apart? Talk to your neighbor. What does that mean about when we pull them apart? If we were to answer this question, for if we were to manually pull those atoms apart, What does that mean about energy being absorbed or released? All right, can I hear from one voice? Is the energy absorbed or released when we pull these apart? Sarah, thanks for volunteering.
Would it be absorbed because it needs energy to pull apart from each other?
Great. So because they're more stable, we're taking it from more stable to less stable. It has to absorb energy, and that's energy we have to put in mechanical energy. In this case, is what I'm doing. Love?
Just like using magnets, like you have to actually pull to
Exactly.
to come out.
And so these have magnets in them, which is why I really like that analogy, is that magnets have a strong attraction to each other. You can actually physically feel that attractive force here, and you can feel that you have to take energy to pull them apart. So let's go back and let's revisit this image that we started out with. All right, we have this flash of lightning, this boom, energy released for cell metabolism. So I want you to discuss with your neighbor if forming a bond between two hydrogen atoms releases energy, what must have to happen when we break a bond? And then does that only apply to this bond? Go ahead and talk to your neighbor. Discussing this question, and then how specific is the answer. Let's go ahead and re-answer this question at the bottom. It's the same question we kind of started out with. Go ahead and talk to your neighbor about how the discussion you just had applies to this question. Did anyone change their answer? I heard a yes. Is that Caleb? Can I hear from someone why they changed their answer? So what's the big challenge here? So we have a quarter of the class changed their answer from before and said that no, breaking a phosphate bond in ATP does not release energy. Why? What was the discussion you had? Can I hear some thoughts from discussions you had about maybe why this wasn't comfortable? What was going on in your discussions? Avery?
We were talking about the role of stability in the whole process, because how we were understanding it was if it was stable, it was going to require some absorption of energy to create that bond being broken, but there was still a little bit of fuzziness on that.
Yeah, so that's a really good point to have a discussion. So if you have, let's say, methane or any other molecule, question is it more stable in this form or not? Are these atoms more stable here than they would be if they were all apart? Why? How do we know that?
Because otherwise they would just fly apart.
They're all together. If they're together, if we find them together, that means they're more stable than not being together, otherwise they wouldn't be together. So the question is, in ATP, are these more stable together or apart, those two phosphates? They have to be more stable together, or else they would just poof, right? So then what does that mean about energy of breaking that bond? How does that relate to two hydrogens breaking apart? Is it different? Is it the same? Talk to your neighbor again for a second. Is it different to break apart two hydrogen atoms or a carbon hydrogen or a phosphate bond?
When you're making DNA and break a phosphate bond. That's your answer.
I got
So I'd really like to hear from some of the discussions. Can I hear from some people who maybe haven't been talking very much today? I want to hear about what you guys discussed. Does this only apply to hydrogen, to carbon, hydrogen? Gail?
I'm not really sure if this applies, but I just remember that if you have an ATP and you break one apart, you release energy. Like,
That's what that image shows.
and then when it's good, you have an ADP now, and when you take another particle to make an ATP again, you absorb energy.
Okay?
So I think it's
So
different.
that's what we're trying to address. So the question is, when we break that bond, is that bond special? Is that bond, is it not more stable when they're together? Aaron, can I hear your guys' discussion?
Well, we were kind of thinking of it as a process, so potentially, like, when you break that bond, it does require energy, but it releases more energy to bond it with something else.
What do you guys think about that?
I think that's perfectly accurate.
That's amazing! High five, air high five. So basically what we've always been taught is that breaking this one bond releases energy, and that's totally and completely wrong. Okay? This is garbage. And the reason it's garbage is because it doesn't talk about the whole process. Hydrogen bonding to hydrogen is no different from an oxygen to a phosphorus in this molecule here. If they're not more stable together, you're not going to find them together. It's just that simple. So if they're more stable together, that means it requires energy to break them apart. So then what's missing? Turns out that ATP hydrolysis requires breaking apart of two molecules. So we break a water molecule apart, and we break apart a phosphate. We have to put energy in for both of those. But then we form multiple new bonds. And does that absorb or release energy when we form new bonds? It's going to release energy, and each of those new bonds that are formed releases way more energy than it took to break in the first place. So it's kind of like putting water up on top of a dam and then bringing it back. Is it going lower or not afterwards? And so this misconception is pervasive across the whole internet, so I just Googled ATP and energy, and across here we see all these flashes of light and not really describing the situation that's occurring. So for the rest of the semester, I want us thinking about if we have an increase in stability, we're going to find things together. We can calculate how much energy is actually released when those atoms come together to form a new molecule. We'll be doing that in a couple of weeks. But then we have to also say, it doesn't matter what the identity of any atom is, whether it's on Earth, whether it's on Mars, if those atoms are together, they're more stable. So pulling them apart has to be a requirement of energy. But in a chemical reaction, we trade partners. We break one bond. Maybe that requires a little amount of energy, and we form a new bond that releases a much greater amount of energy, which is what they're
Like wood burning with oxygen.
Yep, so there's bonds being broken and bonds being formed. So the act of breaking a bond or forming a bond doesn't tell you how big it is, the identity of that bond does. So we'll spend a lot more time on that throughout the semester, but the big takeaways here is that breaking of any chemical bond requires energy, formation of any chemical bond releases energy, and that there's not this magical pin that you can poke a bond and energy poofs out. Right? So the bonds don't store energy. All right, that's part one of our class today. Nice and short, huh? So before I go into part two of our class, I wanted to make sure to mention there is a student group on campus called Young People's Civic Action Committee. This group, I'll take a quote directly from one of its members. This club provides a space where we can freely talk, debate, and gain a deeper understanding of certain issues, cultural issues, environmental issues, political issues, all this kind of stuff, based on facts rather than opinions. And so I'm going to be joining this group tomorrow, and I was asked to share about this group with the class, because you might be interested in engaging with other peers who are inquisitive and want to talk about facts as opposed to opinions, and use that to kind of think about what it is that we do in our lives. So they're meeting in the leadership lounge inside the conference services. I don't even know where this is. I'm going to figure that out. Did you want to add something to that?
Conference services is like when you go to DSC, it's at the top floor, and right before you get to those big stairs that go downstairs, it's like right there.
So the topic tomorrow is going to be on environmental impacts of humans, I guess, past, present, and future. So I'll be talking a little bit about climate change at the beginning, and then it'll be just a discussion forum for the rest of the time. All right, second half of class. We're going to be talking about drawing Lewis structures. If you have not yet completed the chem tour on Lewis structures, please do it. I don't know what else to say. I've talked to a number of people and they either haven't found or haven't done it. Announcement went out Friday with a link directly to the chem tour. That's going to allow us to talk about steric number. It's going to be important for lab you're doing this week. It's going to be much easier to draw Lewis structures in lab if you've actually spent some time thinking about it. We need to calculate formal charge, and we're going to do a whole bunch of other stuff. So let's work on now question number 7 on the front side. For the sake of time, we're not going to click these in. I want you to talk to your neighbor and fill in the 2 things for each family. I want you to fill in what group that family is part of. So the group number on the periodic table, 1 through 8, main group. And then how many covalent bonds you expect each of those groups to form. So you can talk to your neighbor and fill out those 2 things for each of the groups in question 7. So take about a minute, minute and a half to answer this question. More seconds. All right, can I hear from some new voices around class? If we're looking at the carbon family, carbon, silicon, germanium, tin, lead, what group is that? And how many covalent bonds is it likely to make? Can I have a Sarah, Andrews? It's group 4, group 4A, we can call it main group 4, whatever you want to say. And then how many bonds is that likely to form? Why?
You count over until it gets to the octet.
Great, so you can look at the periodic table and you can say, well, if it has 4 valence electrons, we know that 8 valence electrons would be isoelectronic to neon. So it could use sharing of 1, 2, 3, 4 electrons. That would allow it to be in an electron configuration where it looks like it has a full octet. All right, what about the chalcogens? Can I have another volunteer? Ruby?
Group 6.
So it's in group 6 on the periodic table, and then how many bonds are group 6 likely to make?
2 bonds.
Great. What about nitrogen, phosphorus, arsenic, and those ones? Kayla? Group 3? Great. Group 5, and we're likely to fill 3 more bonds in order to get to a full octet type configuration. If you notice the way that we're drawing electrons, we're drawing pairs around the center atom, and that helps us kind of see, well, there's not pairs here. If we do 8 around the central atom, we're likely to have more of a full octet looking kind of thing. What about the last one, the halogens?
1.
Group 7, 1 bond each.
Why is carbon, go back?
Nope. After, I just done it last time. So what I want you thinking about, I want you looking at the periodic table, and I want you thinking about how many s and p orbital electrons there are past the last noble gas. And the way I want you thinking about that is through our quantum description. if you can write the electron configuration for any atom, you can determine how many valence electrons, you can determine how many bonds it's likely to have, and how many unbonded electrons there are. For the next class, you must have worked through the problems in the chem tour on S equals n minus h. It's in that chem tour. We'll be doing a lot of Lewis structure drawing on Friday. You'll be doing a lab this week as well. Thank you. And don't forget to grab one of the forms on the way out if you want to do the exam wrapper. When you turn in the exam wrapper. If you still need your exam, stop by. Nope. Yeah, so I'll set up some other ones. So send me an email with your availability tomorrow, Monday, and Tuesday, and then I'll try to make some extra drops out. You changed your hair. I don't recognize you. I need to announce it. So right now they're I can't remember what my normal are, but I'm gonna add an additional set of office hours. So email me your availability on Monday if you want me to do that.
So sometimes they'll have this, so it's hydrogen, it won't form like one, right? They can only share one. So it's sort of a guessing game. So it's just saying you add a single bond first, and if it doesn't make sense, add a double bond. If that doesn't make sense, you can actually do that. So actually that's how they do it.
How do we, what? So you just don't do it?
No, I mean on the final exam, are we just gonna like show you the work and then you just, how does that go about exactly?
So I have an equation that relates each specific question that you took on the test. So what concepts it relates to on the earlier test, and then I back give you half credit on those questions.
Okay.
What's up, Eric?
I just want to say, I'm starting to notice, pick up on the Veritasium stuff.
Oh, have you been watching his channel?
No, I mean, I've always been watching it.
Oh, okay.
Yeah, but...
Snap us, man.
Yeah.
That's where it's at.
I love it.
Sweet.
I was wondering what points I got on this question.
So it looks like you got 2.5 off here out of 6, is that right?
I got half.
No, you got 1 off there, 1 off there, half off there. So that's 2.5. So that brings you down to 4.5. And then so that means that you got 2 points for this, and it brings you basically cancels out these two.
Oh, I see. Okay, thank you.